Let's talk about a problem in quantum mechanics that is of the infinite square well. So think of this problem as you have a particle that is inside a box, say that it's an electron, in such a way that it is confined in a region of space by these two walls, say, of potentials, right? And the potential is so high at these two walls that the electron is said to be bounded in this region, so it cannot go past these walls, right? Okay, so our task is then to solve the energy eigenvalue equation, that is the Schrodinger's equation for the infinite square well. So the first equation in a box you see is, that is the Schrodinger's equation, and so we will solve that to find out the energy eigenstates, right? Okay, so the potential energy is going to be 0 inside this well or a box, and it will be infinite outside the well, right? So what that tells you is this equation over here, the second box, this one, it says that v of x is 0 in the range for x. X, by the way, is this horizontal axis on this graph over here. So from 0 to L you have absolutely no potential. That means the electron can move freely inside these inside this limit, right? And for x greater than L or x less than 0, right, we have potential as infinite. So that is represented by these two vertical lines over here. Right, so due to the shape of this potential energy function, right, you can call this thing over here as the infinite square well, because it looks like a square, right? Okay, so our goal is then to find out the energy eigenstates as well as the energy eigenvalues of the system by solving the energy eigenvalue equation. We're going to use the potential that is over here described as v of x, right? And using this, we are going to solve the Schrodinger's equation, right? Okay, so a particle is in this potential is then completely free except at the walls, that is at x equals 0 and x equals L, right, where there is an infinite force acting on the particle or an electron to prevent it from escaping the walls, right? So you can immediately tell that outside of the well your wave function, that is psi of x, is going to be 0, right? And that is because the square of your wave function, this thing over here, gives you the probability of finding the particle at position x, right? And so outside the well or this box, it's going to be 0 because the potential is so high that the electron cannot escape, and that implies that you cannot find the electron outside this well. Well, however, inside the well where V is actually 0, right, so the potential is 0, then you will have a non-zero wave function, right? And so the energy eigenvalue equation can be written. Let me go to the next slide and write that equation down here. Okay, so it's negative h bar squared over 2m gradient x with respect to x squared psi of x, right? And this is equal to E psi of x. So this is the Schrodinger's equation, right? And now we can write this, we can write it as a differential equation now by rearranging the terms, right? So del square psi of x is going to be equal to negative 2me over h bar squared psi of x, right? So all I've done is I've rearranged this equation over here and written it down, right? Okay, so now we can make a substitution to solve this differential equation, and let's say that this term over here, that is 2me over h bar squared, right, is some constant k, right? It is k squared, right? So with that substitution, then I can write my eigenvalue, or the Schrodinger's equation, the differential equation, as this thing over here, right? Negative k squared psi of x, right? Okay, so we can then think of k as it's the wave vector, right? And we'll see that later on. Okay, right, so this equation over here, let me box this, okay, this equation over here is actually the equation for a simple classical harmonic oscillator, right? And the solution for this, then we know, is as following: psi of x is equal to a sine of kx plus some another constant b cosine of kx, right? So it's a periodic function, a sinusoidal function, right? And so the energy eigenstate wave functions throughout our space will be then written like this. Let me write it down. Psi of x will be, let's write it like this, okay? So we know it's 0 for x is less than 0, right? So outside the well, and it is also 0 for x is greater than L, again for outside the well. So we don't have an electron outside the well, right? But however, for inside, our solution, as we said, is the periodic solution, that is a sine kx plus some constant b cos kx, right? And this is for your x in 0 to L, right? Okay, so if you look at this equation over here, we have two constants, right, a and b, and so we will use our boundary conditions, that is, or that are, if you look at your graph over here, your psi of x and your derivative of psi of x must be continuous, right? And so then also the continuity of our psi of x, right, it requires that your psi at 0 is equal to psi of a, and or psi of L, right, because this over here is L, so they must be equal to 0. So let me actually write it down over here. So our continuity of psi of x requires that psi of 0 is equal to psi of L, which is equal to 0, right? So it should vanish at these points, which means that then the particle cannot be outside of the box, right? So which means then the wave functions then must vanish outside this interval. So that gives us some information about A and B, right? So we can then think of this as, let me actually put the values in the solution, right? So we had psi of 0 will then be, if you go back here, our psi of x for inside the well is a periodic of sine and cosine functions, right? So we can write it then as a times sine of 0 plus b times cosine of 0, right? And so we know that sine of 0 is 0 and cosine of 0 is 1, so this thing over here gives me b, right? And then this b must be equal to 0. That is following from this continuity equation of psi, continuity of psi of x, right? And so this tells us that the cosine part of our general solution is not allowed because the cosine solution is not 0 at the edge of our box, right? So it does not match the wave function outside the box. And so if that's then the case, then I can write my psi of x is then a times sine kx, right? This thing over here. So let me actually put this in the box. Okay, so the boundary condition at the right side of the box then yields, if you go back here, look at this box, the right side of the box is then psi of L is also equal to 0, right? Because the wave function does not exist at L or after L. And so I can write then this as my psi of L is equal to A times sine KL being equal to 0. So now what I can do is I can do two things. I can either say that my A is 0 or my sine KL is 0. However, for my A is equal to 0, I'll have a trivial solution, right? But for my sine KL being equal to 0, what does that mean? That means that think of KL is now as your theta or a function of sine, right? And at KL being equal to some integer times pi, integer pi values, it's going to vanish, right? So this tells you that your KL is going to be integer pi values. So it can be say 0 times pi, so that's 0. It can be plus 1 times pi or minus 1 times pi, so plus minus pi. And likewise plus 2 times pi or minus 2 times pi, so 2 pi plus minus 2 pi, and well, so on. You get the pattern, right? Well, however, if you think of being k equal to 0, right, is actually not a good thing to happen, right? Because that would just imply that psi of x is 0 and it vanishes. And vanishing of the wave function is actually implying that there is no particle, means that there is 0 probability of finding the particle. And so, but we know that there is a particle inside the box, and so n being equal to 0 is then not allowed, right? Okay. So from this, then we can write our wave vector kn as n pi over L, right? With n being equal to 1, 2, 3, 4 and up to well, so on, right? So the only discrete wave vectors are allowed. This thing over here implies that, right? This thing implies that only discrete values of wave vectors are allowed, and that's because n is 0, not 0 actually, 1, 2, 3, 4, 5, right? And so then this condition is then also known as the quantization condition, right? Okay, and in this expression over here, n is actually the quantum number that is used to label the quantum states and energies, right? Okay, so let's go to the next slide. And if you remember, we wrote our k squared as 2 2me over h bar squared, right? So what we can do now is we can find the value of E from this, and then what would that be is E is equal to h bar squared k squared over 2m, right? Okay, so now let's just substitute the value of k that we just found out in the previous slide, that was k is equal to n pi over L, right? So when we put this value in this expression over here, we get our energy, eigenenergies, En as h bar squared n squared pi squared over 2m L squared, right? And so the wave vector quantization then leads towards the energy quantization. And so here again then n will be equal to 1, 2, 3 and well up to so on, right? And so this is then our eigenenergies, and they are quantized because our wave vector was quantized. Now the allowed energy eigenstate wave functions, as we wrote them previously, were get rid of this, yeah, they were psi of x is equal to a times sine of n pi x over L, right? And again here n is equal to 1, 2 and up to so on, right? Okay, so in this we have to find a, right? We don't know what the value of a is, but what we do know is that the particle or the electron is definitely going to exist inside this potential well, right? That's how we started our problem. So then the probability of finding this particle, right, should be then it should exist if we integrate it from all that space where we know that the electron is there, right? So then this square over here, which is the probability, and integrating it over all space, or say, let's go back to this diagram over here, say from 0 to this L over here, if we integrate it, then we will definitely find our electron in the box, right? And so it's then going to be equal to 1, right? And so if we use this normalization condition, then we can find the value of our constant A, which once we do is actually your modulus A squared comes out to be 2 over L, right? And so with this then we can we finally write our psi of x being equal to under root 2 over L sine of n pi x over L, right? And so this expression over here is our expression for wave functions, right? And we also found out our energy eigenvalues, that were En being equal to n squared h bar squared pi squared over 2ml squared, right? And so this was actually our goal, right? To find the wave functions and the energy eigenvalues for this problem, right? Okay, so technically we are actually done with the problem, but now let's look at some of the things that are, let's interpret these things, right? So the time independent Schrodinger equation has delivered an infinite set of solutions, right? So because n can go from 1 to, well, infinity, right? And so we'll have infinite number of solutions. So if we look at some of these solutions, let's go here and let me try to plot some of them, right? So these solutions will actually look a bit like this. For n equals 1, right, we're going to have something like this, and for n equals to 2 we'll have something like this. I'm not so good at drawing. Okay, so something like this, right? So it will be something like this. Okay, so this is for n equals to 1, this is for n equals to 2, and on my horizontal axis I have my position x, right, and on my vertical axis I have my psi of x, right? So this is how my wave function is going to look like. So what this means is, actually, if you take this wave function and if you for example for n equals 1, right, so you take n equals 1 and you square this, right, and so that will give you the probability. So the probability for n equals finding the particle or an electron will be maximum at L by 2, right, for n equals to 1. And when you go to n equals to 2, at L by 2, the probability will actually vanish, right? So there's a very, very, very lower or least chance of finding the electron at L by 2 for n equals to 2. Okay, so we can now relate our wave vector and the wavelength of these wave functions, right, through a relation that we know for k, that is our k is actually equal to 2 pi over lambda for our wave vector, and just right now we've also said that our k is n pi by L, right? So we found this out. So what we can do now is we can actually equate these two and say that 2 pi over lambda is equal to n pi by L, and from this then what we can find is that my L is actually equal to n lambda over 2, right? So first let me box this thing over here. Okay, so what this actually means is that the well must contain an integer number of half wavelength, right? So that could be 1 by 2 lambda, that could be 3 by 2 lambda, right? Or it could be for example it's 2 by 2 lambda, so then it's just lambda, right? Okay, so well, if you look at this relation or the expression, it is actually the same case as of a standing wave, right, in classical mechanics. Now, the distinction between the classical wave and the quantum wave is that the classical waves do not have quantized energies, right? Okay, so actually that's it for this problem. However, we can look at some of the properties of the wave functions and energies, right? So if you look, if you go back on this graph over here, what you can see is that they're alternatively even and odd, right, with respect to the center of well. So say psi 1 is even, psi 2 is odd, and then similarly you'll have psi 3 even and psi 4 odd, and then so on, right? Okay, and another property or a fact is that these wave vectors are actually mutually orthogonal wave functions, right? These wave functions are going to be mutually orthogonal. So what that means is that if I take my psi 1 and psi 2, right, and I take the dot product of them or the inner product, that is going to be 0, right, if psi 1 and psi 2 are not equal. However, if they are equal, then it's going to be 1. Okay, so another property or a fact is that these wave functions are complete. Complete in a sense that we could write them as a function. For example, say there's a function f of x, and we can expand these in that function as n equals sum over n equals to 1 to infinity Cn psi n of x, right? And then this thing over here then can be simply written as under root 2 over a. All I'm doing is substituting the value for my psi of x, n equals to 1 to infinity Cn sine n pi x over a. Right. Okay, so this means that the wave functions are complete, right? So, well, that's it for our problem. Our goal was to find out the energy eigenfunctions and eigenvalues. And so we found those out by solving the Schrodinger's equation using some particular boundary conditions of the potential. And we can use this infinite square well problem to solve some problems in condensed matter physics that are related to lattice, right? So let's just look, say that you have a lattice of atoms. I'm going to do this over here, right? So say you have lattice of points. You have these atoms over here at these points. And so what we could think of this as that at these atoms there is an actually infinite potential, right? At each of this atom there is some infinite potentials, and so if the electron has to move between these atoms, it will encounter this infinite potentials. So what this means is that we can treat our atoms as some infinite potential barriers, right? Okay, so that's it for this video. I hope you enjoyed and understood what an infinite square well is and how to solve for its eigenfunctions and energies.